Okay, I've started the recording now. Let's start today's session. So, good afternoon, everyone. This is Mrinalini, Research Scholar PMRF from School of Physics, University of Hyderabad. As you all know, this is the interactive session for Experimental Physics First course. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and this is the 11th session. These sessions, as you know already I think, it happens every Saturday 3 to 5. Let's proceed with today's session. So let's have a recap of what are the experiments we discussed in last interaction or the last week. Last time we discussed about platinum resistance thermometer, tried to understand the theory, the working behind it, and then found out the working formula to do the experiment based on platinum resistance thermometer. Another concept that we tried to understand was the current voltage relationship in an LR circuit, and we again found out the working formula for this. Another experiment was on LCR series circuit. We tried to understand how the voltage drop across the resistor and inductor and the capacitor is in phase, out of phase, or lagging behind or leading the current that that is flowing in the series circuit. Another thing that we discussed was sensitivity of ballistic galvanometer. Ballistic galvanometer, that as we had discussed, is used to measure the charge flowing in the circuit, and we had understood the working principle behind it and derived the working formula for measuring charge sensitivity of a ballistic galvanometer. So these were the things that we discussed last week. Now let's proceed to discuss the lectures. The concepts based on this week's lecture, and also we will do the last year's assignment based on these concepts. So the first topic that we'll discuss today is RC circuit. That is when a resistor and a capacitor are connected in series in a circuit, then what happens? Like this experiment related to this concept that was performed in the lecture, as you must have seen. There the aim was to find out time constant of a series RC circuit by charging and discharging method. So first let's again understand the theory of a RC circuit. So if we have a RC circuit, let me draw the RC circuit first. So it will look something like this. There will be a voltage source. Let's keep it a simple battery. This will be positive terminal, this will be negative terminal, and let's make a switch here. This is this end, let it be as this is the resistor that we have connected in the circuit, denoted by R, and this is the capacitor. We are connecting an emitter also, and let's call it like if this is a switch, either we'll connect it with first or we'll connect it with second point, and accordingly the closed circuit will change. Let's call this Q, and let's have a voltmeter across this capacitor, since we want to see what is the voltage drop when we'll be charging and discharging this capacitor. Let's call it's not important, but let's name these points something. This is a capacitor, this is a resistor. They are connected in series. We'll see what happens in this circuit, what happens to the capacitor when we are charging the capacitor. That is when we'll put this switch connected to 1, then this will be a closed circuit. Another time we'll see what happens when the capacitor is discharging. That is when this key we'll connect with 2. That means this will be a closed circuit. So the capacitor will discharge through this resistor. In first case, it's charging through this resistor. In second case, it will be discharging through this resistor. And the voltage source will be disconnected. Okay, so first case, when it's when this switch is connected to first, this is the situation when the capacitor will be charging, right? At time t is equal to 0, like just before we connect this, charge on the capacitor will be 0, right? Now we know, okay, let me write here, the total voltage drop, this is at t is equal to 0. After it's connected, then what will be the, so this, let's call it V0, this is the source voltage V0. Then what will be the total voltage drop in this circuit? It will be equal to the source voltage, right? So this is source voltage, and the voltage drop in the circuit will be voltage drop across resistor, that will be current, because the current, it's a series, everything is in series, so the current will be same throughout the loop. So the voltage drop across resistor will be I times R, and there will be voltage drop across capacitor, that is Q by C. If you remember earlier when we had discussed about capacitors and inductors and resistors as components, like what are the different components available in lab, that time we had discussed about capacitors in series, when it's in parallel. So we know capacitance of a capacitor is given by charge stored and per unit voltage applied. So this will be the total voltage drop in this circuit. Now since we know current is given by rate of change of charge, right? Yeah, flow per unit time, flow of charge per unit time, that is I is equal to dq by dt, right? So this equation will change to, and if I divide this equation by R, then it will become V0 by R is equal to I plus Q by RC, and putting the value of I in terms of charge, I'll get V0 by R is equal to dq by dt plus Q by RC. Okay, now we'll do some rearrangement and write everything I want to write in the form of derivative. So if we'll take it one side, then, and if I as I said, we'll rearrange, we'll get something like this, 1 over RC. From here we are getting, because even when I'll take derivative of this, it will be 0, so we can write it like this. So even like so, yeah, we can comfortably, I mean there's nothing wrong when we write it like this, because derivative of this will be 0, so it's correct. And 1 over RC, which you can see here, 1 over RC I'll take, then it will become V0 C, right? So it will be Q minus V0 C is equal to 0. Since you can see, if this I take as Y, okay, because I wanted it to be a single variable differential equation, so we have taken it like this. Then this becomes dy by dt plus some constant, and y is equal to 0. So this is a first order differential equation, which when we'll solve, the solution that we'll get for this equation, the solution for this equation will be this y. Y is what? Q minus V0 C will be equal to A times E minus T by RC. Okay. So this is the solution for this equation. Now with boundary condition, this is also a boundary condition, that at t is equal to 0, the charge was 0. Using this boundary condition, And let's have another boundary condition also. Another boundary condition will be that at t is equal to infinity, when the loop is closed for a long time, that times the charge will reach the maximum amount possible. It's slowly charging, the capacitor is charging, and it will reach to a value that is maximum possible based on this thing. So based on these two boundary conditions, we'll get the charge, the expression for how much charge is there on the capacitor after a certain time t. The expression we'll get, this is also actually amplitude. So final expression let's have, because the boundary condition when you will put, you will get the value of a, that when you will substitute, you will get this final expression. In detail, you can again watch the video lectures. Here we are just doing the recap. In case if anyone has doubt, they can ask. Otherwise, let's do it fast so that we can move to the assignment questions. So this expression that we will get is q naught minus e to the power minus t over rc. So this is the expression of charge while the capacitor is charging. So at any time t, the charge on the capacitor is given by this expression. This is while charging. Okay. Now the next thing, let's see what happens in a series RC circuit during discharging. So as I said, in this equation, in this circuit, when it's connected, this S1 is connected, that is the battery is there in the circuit, that time it's charging. Now we'll disconnect it from this point and connect to this point, means this small closed loop will be the closed loop. So here there is no battery, but there is a resistor, so this capacitor will start discharging and the current will start flowing. As you can see, earlier the current was flowing in this direction and it was charging this capacitor. Now the current will flow in this direction and it will discharge through this resistor, and the current will flow through this resistor in opposite direction now. So when this switch is connected to 2, now the situation is the capacitor is discharging. Okay, what happened? Sorry, something happened. I'm sorry. Just give me a moment. Sorry, it seems, yeah, now I think it's working. Something had happened with the pen. Okay, what happened? Anyways, yeah, now it's working. So let's continue. So what is the case when the capacitor is discharging? Capacitor is discharging. When the capacitor is discharging, the voltage drop here will be across the resistor, right? And what will be the voltage here? That will be the source. So the equation will be IR plus Q by C equals 0. Again, putting I is equal to dq by dt and dividing whole equation by R, we'll get it like this, dq by dt time, okay, and dividing by R as I said, so it will become Q by RC is equal to 0. Now again, this is also an equation with y is the dependent here. So what will be the solution? The solution will be Q is equal to A e to the power minus t over RC. Again, using the boundary condition, what will be those boundary condition? That at time t is equal to 0. Now since this is the situation case of discharging, that means at t is equal to 0, the capacitor is charged with the maximum charge possible. So at t is equal to 0, the charge on capacitor is q naught, that is product of C and voltage is maximum. So using this, when we'll put this boundary condition here, that at t is equal to 0, let me just show. At t is equal to 0, q is q naught. So q naught will be, at t is equal to 0, q is q naught a, and t is equal to 0 means e to the power 0, that is 1. That means a is q naught. So we'll substitute this here. So the expression becomes this, e to the power minus t over rc. Now actually so for charging case also, actually we should have discussed that what happens to the voltage variation or the current variation in the circuit when the capacitor is charging. So when the capacitor is, again let's go to charging condition, when the capacitor is charging, so from this expression we know q will divide everything by C, then we'll get q by C is V, voltage drop, right? So writing from there, we'll get that voltage at any time t in the circuit will be given by this expression, or sorry, on the capacitor will be given by this, T over RC. And the current flowing in the circuit, which is time derivative of charge at any point, since we know the expression for charge is this. So the expression for current will be derivative when we'll get let me write the final expression, e to the power minus t by RC. So this is how the voltage will vary during charging, and this is how the current will vary during charging of the capacitor. If I draw it in a graph for current versus time, the current in the circuit will decrease with time exponentially. As you can see, the exponential factor is there, so it will decrease exponentially. And for voltage at any time t, at t is equal to 0, it's I naught, actually some I naught, and after that it's exponentially decaying. For voltage, it will be exponentially increasing and then reach V naught or some maximum value. It exponentially increases. So this is what happens for charging. For discharging, this is the charge at any time t. The charge on the capacitor or the charge flowing in the circuit is given by this expression. From this, we will get the expression for I also at any time t, which will be minus I naught e to the power minus t over RC, and the voltage in the circuit will be given by V naught e to the power minus t over RC. Here for the current, the negative sign shows that while charging, the direction of current was opposite, and while discharging, the current flowing in the circuit is in opposite direction. So this is what the negative sign shows. So this is the expression while the capacitor is discharging for current and voltage at any particular time t for the circuit, in the circuit. And the graph for these will be as while discharging, it will be ticking like this. Oh, another thing, wait a minute. So yeah, another concept that we want to, the time. Okay, so these were the expressions that we found. Now as the aim of the experiment was about finding out time constant of a RC circuit by charging and discharging methods. So what do we mean by time constant? So time constant is the time required to charge the capacitor through the resistor, of course. So time required to charge the capacitor from initial charge voltage of 0 to approximately 63% of the value of applied voltage, or to discharge the capacitor through the same resistor to approximately 37% of its final charge voltage. What does it mean is that time constant of an RC circuit we define as the time required to charge the capacitor, time required to charge the capacitor up to 1 minus 1 by E times the maximum charge, which comes out to be 63% of the maximum charge, or to discharge the capacitor to 1 over E of the maximum charge, which comes out to be actually 37%. Yeah, 37%. So the time required is known as time constant of the RC circuit. So when we are charging, we know that current is decaying, right? It's given by this expression. The expression for charge was here, and it's charging, sorry, the charge is increasing, and it increases. It will go to this point, the full, when it's completely full, but at some 63.2%, when it's 63% of the full that it can reach, that time, if I plot charge versus time, and that time will be called the time constant, denoted by tau. Similarly, when it's discharging, so the charge will decay, and at some time, again called time constant, it will be 1 by E. Here it will be 1 minus 1 by E times Q naught. Here it will be 1 by E times Q naught. So this is called the time constant. So you can refer to what was the experiment in the lectures. It was very nicely performed and demonstrated. Now let's do the questions based on this. One more thing, this tau time constant is actually the product of resistance and the capacitor value. So this is time constant formula. Now let's start doing the questions. So what is the dimension of, the question is, what is the dimension of product of resistance and capacitance? So resistance R and product of resistance and capacitance means RC. We want to find out dimension of the product of resistance and capacitance. Now let's make it to a different version where we know easily the dimension of those units. Let's take this R and C product to that form. So R and C, let's keep it like this. Now capacitance, we know capacitance is charge per unit voltage applied. So this will be Q upon V. Now we know charge is current times the time, right? Because current is dq by dt or q by t. So Q will be I times t. Voltage is also I times R. So what we are left with is time. That means the dimension of product of resistance and capacitance is equal to the dimension of time. Dimension of time we know is just t, right? So that means if we write with all these M, L, T, A, it means we can write as M is 0, L is 0, T is 1, and A will also be 0. This will be the correct answer, not this. Yeah, this is the correct answer. So answer B is correct. Next question is, what is the dimension of quality factor? So quality factor represented by capital Q for RC circuit, if we talk about it, quality factor is the ratio of inductive reactance to um, resistance. It's the ratio, so basically it's the ratio of resistance to resistance, so it's dimensionless. And since for RC circuit it's this inductive capacitance divided by resistance, so it's dimensionless, so dimension will be nothing, it's dimensionless. Now the next question, keeping all other parameters unchanged, if R of the LCR circuit increases, then the quality factor. So quality factor, as I told, is the ratio of resistance, the inductive reactance or the capacitive reactance, divided by the resistance of the, something is wrong, just okay, I think some technical glitches is happening, but anyways, okay. So as we showed it for as I said for CR circuit, so for LCR circuit also it will be dimensionless, but what will be this thing for LCR circuit, and it's asked if R of the circuit increases, then the quality factor, since quality factor is inversely proportional, like for LCR circuit, if we say that it's sorry, let me make put it in representation. Let's say it's chi L or chi C, then it will be omega L divided by R. So the question here is, if R of the LCR circuit increases, if this increases, then the quality factor, as we can see, will decrease. So the quality factor of the LCR circuit will decrease with the increase in resistance. Next question is, a capacitor of capacitance C and initial charge Q0 is allowed to discharge through a resistance R for time t. If the time is 2CR, then the charge remaining on the capacitor. Okay, so we know, so this is the situation for a discharging capacitor. Here the capacitor is discharging and we have been asked what will be the charge remaining on the capacitor after time 2CR. So we know the expression of charge remaining on capacitor during the discharge cycle. So the expression for charge is given by Q0, that is the initial value, which is the maximum amount of charge that can be stored on the capacitor, and the exponential factor. Right? This is the expression during discharging of a capacitor. Now since the time the question is asking what will be the charge remaining after time 2CR. So substituting this will be Q0 e to the power minus, time is 2CR divided by this. So this means this is Q0 e to the power minus 2, which is Q0 divided by E square. So the charge remaining on the capacitor is Q0 over E square. Yes, option B is the correct answer. Now the next question, a fully charged capacitor, the charge on it is Q0, is discharged through a high resistance. The nature of variation of charge remains in capacitor with time. It's the same question as we had done the last one. While discharging of capacitor, the expression of charge at any particular time will be given by the maximum at time t is equal to 0 and the exponential factor. Okay, so the question is the nature of variation of charge that is remaining in the capacitor at any particular time. we know this is exponential factor, means the variation of charge will be exponential. This is linear drop, this is not exponential, this is exponential. So the charge variation in the during discharging of the capacitor, it will be given by this graph. This is the correct answer. Oh sorry, there are no option. Let's take, this is A, this is B, and this is C. Oh, this figure 1, figure 2, figure 3 is written, sorry. And I think A, okay, then there is no problem actually. This written so small that it was less visible. So figure 2 is the correct answer here. Now next question, it's about the previous question. If I naught is the magnitude of maximum value of current, then the relation between I naught and Q naught is, again recalling the expression for charge during discharging, is Q naught e to the power minus E over RC, and now they are asking what will be the expression of current in this circuit. That will be I, we know, is dq by dt, and we will take derivative of this. Q naught will be constant, this will be E, this will be exponential of derivative of exponential is this remains, and then we will take derivative of this, which will be minus 1 over RC. Q naught over RC, and there is a negative sign as well, and the exponential factor. We need to find out, okay, this Q naught over, now we are given at t is equal to 0, at t is equal to 0, I naught is the maximum current, so current is I naught. So with this boundary condition, this equation will change, right? When we will put this boundary condition in this equation, it will become that at t is equal to 0, the current is I naught minus Q naught over RC, and t is equal to 0 means e to the power 0, which is 1. So Q minus Q naught over RC is actually I naught. Putting this value that we have obtained here, if we insert, I'll get the expression for current as I naught e to the power minus t over RC. So the current will also be decaying, but what we have to finally find out is, we have been asked current relation between I and Q. Oh, so we don't need to do this. We just need to tell the relationship between the charge and the maximum charge and the maximum current, which is this. And since we have been asked just the magnitude, so we can ignore this negative sign, and the relation between I naught and Q naught will be, if ignoring the magnitude as asked in the question, it will be this, which is Q naught over RC. This is the correct answer. Next question is, capacitor of capacitance 10 microfarad is fully charged. So the capacitance is 10 microfarad and is charged by 2 volt power source. The charge on a capacitor falls to 25%. So charge on the capacitor falls to 25%, 25% of its initial value. Initial means the highest on it. 25% of Q naught means this will be 25 by 100 of Q naught. This will be Q naught by 4. 25% of Q naught means 1/4 of its initial value in 1 minute. So this is happening in 1 minute. This discharge is happening in 1 minute means 60 seconds. When it is discharged through a high resistance, find the value of this resistance. So it's like a capacitor is there and it's discharging through a high resistance, and we have maybe earlier there was a voltage source, now we have disconnected, and we know that in time t the charge falls to 1/4 of its initial value. So based on this information, we have been asked what is this resistance. So again, using the information that we know, the expression of charge when the capacitor is discharging, using the same formula, we'll be able to solve this. Okay, so Q naught, what will be the value of Q naught? Actually, we know C is Q by V, right? So at the time t is equal to 0, when the charge is maximum, it will be Q naught by V naught. From here we'll get Q naught is C times V naught. Putting this here, C V naught e to the power minus, now this time is 60 seconds. And okay, let's put the values also. C is 10 microfarad, micro means to the power minus 6. V naught is 2, initially it will be 2 volt. And okay, let's get, or wait, yeah, it's fine. Maybe we don't need to find this out also, because I think just by putting the value also I could have done this, because ultimately I need to find out this R, which is in the power. So we can clearly see we need to take the log, natural log on both sides. So okay, let's keep it aside, maybe this is not required. I'll put at time t is equal to 60 seconds, what is the charge? The charge is 1/4 of Q naught. Which is Q naught e to the power minus t over RC. So this will be cancelled. And if I take reciprocal, this will become 4. This will become e to the power t by RC. Now taking natural log on both sides, natural log of 4, let me write, natural log of 4 is equal to t over RC. From here again I'll take reciprocal, so it will be 1 over natural log 4 is equal to RC by t. Since we need to find out R, we'll send everything other side. R will be t divided by C times natural log of 4. Let's see, t is 60 seconds, capacitance is 10 microfarad, and value of natural log 4, let me just calculate what is this. Using our scientific calculator, we'll get this function. Natural log of 4 is actually 1.386. This is the value. Let's solve this. This will give 6 divided by this. 6 divided by 1.386. Oh, sorry. 6 divided by 1.386 is 4.329, and we have in denominator this power of minus 6 that will come up and become 10 to the power 6. So resistance is in ohms, in mega ohms. This is 4.329, 10 to the power 6 is mega. So this is 4.329 mega ohms. The correct answer is C. Okay, next question. A 10 microfarad capacitor is charged to 5 volt and then discharged. Again the situation is for discharging, and the capacitance is 10 microfarad, and the resistor this time they have told 5 mega ohm, and it's getting discharged. It was charged up to 5 volt and now it's discharging. How much charge will remain in capacitor after 150 seconds? Again, it's very simple, using this very useful expression. So Q naught e to the power minus t by RC. So in 150 seconds, how much charge will remain? We need to find out this q after at 150 seconds. So initially q naught will be c. Here we need to calculate this. Yeah, we need to calculate this. Q naught will be c v naught. So c is 10 microfarad minus 6, and v naught, initially the voltage was on capacitor across, the voltage across capacitor was 5 volt. So q naught is 50 microcoulomb, actually this is microcoulomb. So here it will be 50 times 10 to the power minus 6 e to the power, now t is equal to 150 minus 150, and R is 5 mega ohm. Let me just write it here. RC will be 5 mega ohm, means 10 to the power 6, and the capacitance is 10 microfarad, right? 10 microfarad, yeah, capacitance is 10 microfarad. So 10 minus 6, this will be 10 to the power 0, that is 1, and product of R and C will be 50. This will be 50, so this will be 3. 50 times 10 to the power minus 6 divided by, this becomes e to the power 3. So let's solve this. What is the value of e to the power 3? Again, using the scientific calculator, e to the power 3 is, so will be 50 times 10 to the power minus 6, and e cube will be 20.0855. So 50 divided by this value, 50 divided by 20.0855 will be 2.4894, and this is there, so this will be microcoulomb. So the charge remaining after 150 seconds in this particular circuit will be 2.49. If we take round off to 100th decimal digit, it will be 2.49 microcoulomb. So the correct answer is option D. Now we have one more question. Question is, a 5 microfarad capacitor is connected to 12 volt. So this is 5 microfarad, and this this is 5 microfarad. The capacitance is connected to 12 volt DC source through a resistor of 2 mega ohm. This is 2 mega ohm. Calculate the current in the circuit after 10 seconds. So it's charging basically. So the current will, what will be the current at t is equal to 10 seconds. So we know while charging of the capacitor, the current initially is maximum and then it starts reducing. So after 10 seconds, what will be the charge flowing in the circuit? So the expression for this will be, during charging the capacitor, the charge, how the expression for charge we know. During charging, this is, earlier the questions we did, we were dealing with the discharging situation. Now this is the charging situation. Okay, so the charge at any particular time is given by this q naught 1 minus e to the power minus t over RC. Since current is dq by dt, so current will become q naught by RC e to the power minus t over RC. So clearly we can see it will be exponentially decaying. Now after 10 seconds, what will be the charge in the circuit? After 10 seconds, the charge will be q naught over RC e to the power minus time is what? 10 seconds over RC. Now we can either I can just Q naught. What will be the value of Q naught? Q naught will be CV naught, right? And this will be RC. So C will cancel. E to the power minus T. What will be RC? RC. Resistance is 2 mega ohm. Capacitance is 5 microfarad. This will give 1. 2 times 5 is 10. So this will be 10. So e to the power minus 1. This will be V naught over R times e to the power minus 1. Right? Now V naught is 12. V naught is 12 and R is 2 mega ohm, and this is 1 over E. 2 times 6. Now 6 divided by E. What will be 6 divided by E? 6 divided by E is 2.2073. 2.2073, and this will go in the numerator, then become micro, and since it's a current, the unit will be ampere. 2.2, if we have to round off to up to first decimal digit, then this will be 2.2 micro ampere. Okay, so these were the questions based on RC circuit. Now let's move on to another concept, which is based on this we'll do experiment. So this concept is about magnetic field along the axis of a circular coil. So before moving on to this, let's first recall, we had earlier also discussed and done questions for Biot-Savart's law. Again, let's recall what is it. So Biot-Savart law, I'll make first a diagram what it says, then I'll explain what it says. So if we have a current carrying conductor, the shape doesn't matter, but this is a current carrying element, and one end of it, let's call it X, another end let's call it Y, and this is some point around it, let's call it O. Then if in this current carrying conductor we'll take a small length element, let's call it delta L, and we can also denote it as PQ. The distance between this point O and this length element, let's call it small r, and the current in the circuit is small I. Then what Biot-Savart's law says is that when we have a current carrying conductor like this and current I is flowing in it, then due to small current carrying length element delta L, the magnetic field produced at say point O, the magnetic field produced at point O due to this small length element carrying current I, the magnetic field is directly proportional to the current flowing in it, the length of the small element, and inversely proportional to the square of the distance between those 2 points. And yeah, actually there is expression of sine theta also. So xy is the current carrying conductor, PQ is the length element, I delta L is current element along PQ, R is the distance from our point of interest to this length element, sine theta is the angle between this current carrying length element and R. This is the angle between this theta. So it depends, but the magnetic field at point O due to this will be given by this expression, and when we replace this constant, we get if we replace this proportionality constant, we get when we replace this proportionality sign, we put a proportionality constant here. the proportionality constant is given by actually mu naught over 4 pi, whose value is 10 to the power minus 7. So this will become I delta L sine theta over r square. This is Biot-Savart law. Now let's move on to what will be the magnetic field along the axis of a circular coil. This was just because of a conductor carrying current. Now what will be the magnetic field due to current carrying circular coil? Let's consider a circular coil. This is also carrying current I, and we want to find out what will be the magnetic field at point, let's call it P, and it is actually on the axis of circular coil. This we want to find out what will be the value of magnetic field at the axis. So this is the axis of the circular coil, and let's say the current I is flowing in it, and this is some length element delta L. Okay, when we connect this, the distance A it is, which you can see here. If r is the radius of this loop and the perpendicular distance between the center of this current carrying conductor and this point of interest, if this is x, then this will be, since this is a right angle triangle, this will be x squared plus r squared root of it. Okay, now because of this particular length element, actually there will be magnetic field in this direction, and then if we take a similar length element in diametrically opposite direction, the same length element, the current also is same. Because of this length element, if we will see, because of this length element, there will be magnetic field along this direction. Okay, for these two opposite length element, if we resolve the magnetic field values in cos theta and sin theta, we'll see that, okay, so let's make this angle phi. Okay, so this will also be phi, this also be phi. So this will be cos phi and this will be h prime cos phi. They will cancel each other, but this component, which is h sin phi and h prime sin phi, they will remain. So resultant will be in this direction. Similar way, different length elements and their diametrically opposite length elements will have magnetic field in opposite directions, not opposite, sorry, their components, cos phi components will cancel and sin phi components will result in this direction. So ultimately what will happen, this circular current carrying coil, due to this, the magnetic field will be along the axis of the coil in this direction, along the axis, and the expression here is given by this. The h or b we can denote will be given by mu naught over 4 pi. This is the current, this is the perimeter of the coil, times r divided by aq. If this is just a single turn coil, then this is the expression. If the coil consists of n number of turns, then the expression will change to, we'll multiply it with n. And if I only want to write in terms of x and r, then this will become mu naught over 4 pi I n and 2 pi r divided by a cube. I can write as x square plus r square 3 by 2. As you can see here, we can cancel this also, there. Then this becomes mu naught over 2 I n r square divided by x square plus r square to the power 3 by 2. This will be the expression for the magnetic field at point P due to the circular current carrying coil. Now what will happen if this magnetic field expression that we have found out, it is on this axis of coil, right? So what will be the value when it is at the center of coil? That is also the axis of coil, but then this x will become 0. So when x is equal to 0, that is the point P is at the center of coil, then the magnetic field expression becomes mu naught over 2 I n r square, and this x will become 0 means r square 3 by 2, that means r cube. Again this will become mu naught over, this will reduce to I n divided by r, so the expression will be mu naught I n divided by 2r. This will be the magnetic field at the center of this current carrying coil, which has n number of turns in the coil. So the experiment that was discussed based on this was using something called Helmholtz coil. Helmholtz coil. That what is the use of this concept when we want to use some magnetic field source in our laboratories? So we need, either we can use some permanent magnet, or we use this current carrying coil concept to generate uniform magnetic field. So how do we do that? So there is the Helmholtz coil, looks like this, that they, as we discussed the magnetic field variation for this one particular coil, right? So in Helmholtz coil setup we have two coils, and actually the distance between them is half of the radius. They both are of same radius, and the distance between them is half of their radius. In this situation they generate the nearby region has almost uniform magnetic field. So in lab, instead of using permanent magnet, we use Helmholtz coil to produce uniform magnetic field. So let's see how that happens. So yeah, when we have two coils, let's call it coil 1, this is another coil of same radius, they are of same radius, and we want to see what is the expression of magnetic field because of both the coils along the axis. So yeah, the diagram I have made is not good, but the radius for both is same, which is r. Then for coil 1, let's see what will be the expression of magnetic field. So let's call the magnetic field due to coil 1, let's call it H1. Then H1 at the center, that is x is equal to 0, right? What will be the magnetic field? What will be the magnetic field at the center of coil? It will be mu naught over mu naught divided by 2 I n over r, as we had seen in last slide. Now what will be the expression of H1 at x is equal to r by 2? Let's say it's somewhere here. So at x is equal to, if I'm calling the distance, it is some distance x. Then when x is equal to 0, that is at center, this is the expression of magnetic field. When x is equal to r by 2, then what will be the magnetic field because of coil 1 only? This value will become, I'm just directly writing instead of deriving, it will be 2 and I n 8 over root 125 1 over r. Give me a minute. So this is the expression, and then magnetic field due to coil 1 at x is equal to r. If the coil Okay, if we want to see the position, the magnetic field at x is equal to r distance, then the expression that we'll get is mu naught over 2 I n over I n over r. No, sorry, there will be root 8 also, and this will be root 8 times r. Now the same way, because of coil 2 at center of coil 2, what will be the, it will be same due to coil 2, the magnetic field at x is equal to r by 2. It will be mu naught over 2 I n 8 over under root 125 by 1 over r. The magnetic field due to coil 2 at x is equal to r distance will be mu naught over 2 I n over under root 8 times r. So this will be only because of all these different positions, but because of only coil 1. Here these expressions are the magnetic field at different position along the axis, but only due to coil 2. But what will be the at any particular position along this axis, what will be the magnetic field because of both of these coils? That is what we want to find out ultimately. So the expression, the sum of these will give, oh, we don't have space much, let me take one slide actually. So the sum of both magnetic field at a point at center will be h1 plus h2 is equal to mu naught over 4 pi, or yeah, this will be better, we can write 2 plus 2 I n divided by r. So this actually is, as you had seen, we had coil 1, coil 2, right? So if this is coil 1, this is coil 2, if I am trying to find out the magnetic field at this point, then for this coil it is at its center, so the expression here will be 1. For this coil it is at distance r, okay, this is actually passing through the center of both coil. So for coil 2, this point q is at x is equal to r distance, right? For this coil 1 it is at its center, so for this we know at x is equal to r it will be root 8 times r. So this will be r, I have taken common, this means this will be root 8. This actually, this expression if we will solve, it will be come out to be around this 4 by 3 times these mu naught over 2 I n by r. Similarly, at x is equal to r by 2, that is some distance between, okay, at x is equal to r by 2, this whole thing is r, let's say, and this is r by 2 at center. What will be the magnetic field due to both current carrying conductor coil? This was at say q point. The expression will be same for this, let's call it q prime point. The expression will be same for q prime point also, because when we will see what will be the magnetic field at q prime point, then it will be center for coil 2, where it will be at distance r for coil 1. So the expression will again be same. That means at both these points the magnetic field is same, and now we are checking what is the magnetic field value in between these two, Q and Q prime. So let's say, let's take this at r by 2. So the total magnetic field at r by 2 will be given by mu naught over 2 I n over r, and the expression here will be this 8 over 1 root 5, 8 over 1 root 5, right? That means it will be 8 over under root of 125 times 2. When we'll solve this, this will also give 4 by 3 times this values. So what this tells us basically is that at point Q also the magnetic field, the total magnetic field is same. At Q prime point also the magnetic field value is same, and in between also the magnetic field values are same. So it shows that we can use this to produce a uniform magnetic field. Uniform magnetic field we can produce using this setup of circular coils, and this setup is called Helmholtz coil. And the magnetic field, if I show you how it varies, it is like this. So because of only coil 1, since it's inversely proportional to R, right, the expression, so it's a maximum when I mean it's decreases with x. It depends on x, as you see here. Okay, in terms of r here we have written, but this is the distance, and the distance is minimum, the value is high. When the distance increases, the denominator increases, means the magnetic field value is decreasing. So for coil 1 only, the magnetic field variation is like this, that as it's uniform on both direction. Its value is maximum here, and then it decays as we move away from the center of coil. The same way it will go. This is due to H1. This is H1 variation. For coil 2, that is H2, again it's same, that in both direction it will be similar way it will vary, and it's maximum at the center, and it starts decaying as we move away from the circular coil. And the resultant of both H1 and H2 is actually this. So in this area, that is in between this Helmholtz coil, we get as you can see, a very uniform magnetic field, and we can use it for generating uniform magnetic field for small experiments in our labs. So based on this, we had some experiments were discussed. You can see refer the video lectures for these experiments, where we are trying to find out the radius of these coils based on, we were using a magnetic probe to see change the distance, and then see at what distance what is the magnetic field. Based on this, we did these 3 experiments. So you can refer to see what are the details of these experiments. Please refer the video lectures. Now we'll move towards another concept, which is induced e.m.f. of inductance coil. So we need to understand what is Faraday's law of electromagnetic induction for this. Faraday's law says that whenever a conductor is placed in a varying magnetic field, like say we have a source for magnetic field, and there is magnetic field throughout here. In this region there is magnetic field. When a conductor, this is a conductor, is placed in varying magnetic field, and EMF is induced in the coil. So how here it will vary if we move this conductor, or if we move this magnetic field source, then the magnetic field will be varying with respect to the conductor. So in this varying magnetic field situation, when the conductor is placed, an EMF, electromotive force, is induced in the conductor, and if the conductor circuit is closed, if the inductor circuit is a closed circuit like this, then we can also detect current flowing in this conductor, and this current is called induced current. This expression actually is that the induced EMF in this kind of situation, as the induced EMF is proportional to the rate of change of flux. What is this flux? This is magnetic flux. There is change in magnetic field, and that if we take the cross section area perpendicular to this direction of magnetic field, that is, if this is our area that we are considering, then B dot A, this is given by this is called magnetic flux. The magnetic field passing through this perpendicular area is called magnetic flux, and this EMF induced is proportional to the rate of change of magnetic flux and the number of turns in the conducting coil like this. Now there is another law also, something related to this, which is Lenz's law. Lenz's law tells us that the induced EMF induces a current whose magnetic field opposes the change in magnetic flux in order to ensure that the original flux is maintained. So Faraday's law here, first it's telling that EMF is induced because of this varying magnetic field. We are seeing induced EMF and thus induced current in a conducting coil. But Lenz's law is saying that this induced EMF actually opposes the change in magnetic flux. It's opposing the change in magnetic flux to maintain the original flux. And since it's opposing, we get a negative sign. If we write it again, the EMF induced is actually negative. And there is dF by dt. If we take proportionality constant to be 1, we will get this. So it tells us the direction of this EMF induced. And this Lenz's law is also called Faraday's law of electromagnetic induction. This is the same version, but here it tells us the negative, about negative sign also. Now, as we discussed, the magnetic flux is B times A. So that yeah. As I said, this magnetic flux is magnetic field passing through the perpendicular area. So if you are aware, we something called area vector. If the area is like this, then its area vector will be in this direction, perpendicular to this. And since area vector and magnetic field are parallel, B dot A means it will be cos 0, the angle between B and A. So area vector is also in same direction as magnetic field. So B dot A will be BA cos 0 degree. Cos 0 degree is 1. So magnetic flux will be BA. Thus EMF induced will be minus d by dt NBA. Now for a long coil, we have a inductor coil which is has length L, say, and the current flowing through this, let's call it I, and it has n number of turns, let's say. Then the magnetic field produced in this inducting coil will be given by this expression, mu naught, which is permeability of this material, times the number of turns, current divided by the length of this inductor coil. If I is the AC current flowing through this inductor coil, if it is AC current, then the expression we can always write it like I naught sine omega t. Omega also, if I want to write, is 2 pi times frequency. Then this I can write it like this, right? So this is the AC current that we are sending through this inducting coil. Now this is the expression of the magnetic field because of this inductor coil. Now if we place another induction coil inside this inductor coil, actually it's called solenoid. It's called a solenoid. If I place another induction coil inside this solenoid, then as you know, this current is passing, is generating magnetic field around it, And now in that magnetic field, if some conductor is coming, so there will be EMF induced in it. So if what will be the expression? The expression will be EMF minus d by dt, and the magnetic change in magnetic flux times number of turns. This magnetic flux and this B, if I substitute, it will be minus d by dt Na, because here it will be phi. Yeah, this is the equation, right? This is number of turns. Phi is B by A. Okay, so Na, yeah, this will be mu naught Ni naught by L sine 2 pi ft. And when we'll take derivative, we'll get the final expression as minus 2 pi f Na mu naught Ni naught cos 2 pi ft divided by L. Because of this solenoid, when we place another induction coil inside it, the induced EMF in that induction coil will be given by this expression. So we had experiment also based on this induced EMF coil, induced EMF of inductance coil setup, that again you can refer the video lectures for this. And now let's do the questions based on these concepts that we have discussed. So the first question is, if we have a solenoid of length 40 centimeter, okay, so length of solenoid is 40 centimeter and number of turns is 2000 turns of wire. It carries a current of 5 ampere. Current inside is 5 ampere. Then what is the magnetic flux density on the axis of solenoid at middle? So everything is in SI unit, so let's convert this also in SI unit. This will become 0.4 meters. Now the expression for magnetic field due to a solenoid we know is mu naught Ni by L, where N is the number of turns. So this expression tells the magnetic flux density everywhere around the solenoid. So on the axis, around, outside, everywhere. So whatever you want to find out, the value will be same. And the value will be, it's independent of the position of interest because it's uniform through all over the solenoid. So just putting the values, mu naught is actually 4 pi times 10 to the power minus 7, number of turns is 2000, current is 5 ampere, length of solenoid is 0.4 meters. Solving this, okay, this will be, okay, we don't need to find out the actual value, we can just keep it in terms of pi. So if I do this, this becomes like this, 4 will cancel, we'll be left with pi, 5 2s are 10 and 3 zeros, and because of this one more 0, and then we have 10 to the power minus 7. So this is 2, 3, 4, 5. This is 10 to the power 5 and this is minus 7. That means this is pi times 10 to the power minus 2, which equals pi over 100. So the correct answer here is pi over 100. Our next question is, calculate the magnetic field at the center of a circular coil of radius 3.14 meter, number of turns 500 and current is 10 ampere. Magnetic field is the center of circular coil. Here we are talking about the circular coil. We know the magnetic field because of circular coil is mu naught over 2 I n, or capital N, we can call anything, divided by the radius of the circular coil. This will be mu naught is mu naught is 4 pi 10 to the power minus 7 divided by 2. Radius is 3.14, and number of turns, current also we need 10 amperes, number of turns 500. So this pi 3.14 is also pi, we can cancel like this. This will be 2 times 500 means 1000 times 10 to the power minus 7 times 10, right? This will be 3, 4. So 4 minus 7 means 10 to the power minus 3. 4 minus 7 means minus 3 Tesla. It means this is 1 milli Tesla. This is the correct answer. Next question is a time varying magnetic field given by, where is my pen? Oh, yeah. This is the time varying magnetic field exists in a region where a coil of area 50 centimeter square. Area of coil is 50 centimeter square having 200 turns is placed with its plane perpendicular to the field. So we have a coil placed in a magnetic field which is varying, and the expression is this. So the question is magnitude of, of course, since the magnetic field is varying in this conducting coil, there will be EMF induced. So we need to find out what will be the EMF induced in the coil at t is equal to 1 second. So EMF induced, if we only talk about the magnitude, it will be d phi by dt. And what will be phi? It will be d by dt of B, A, and number of turns. A and N are constant. Magnetic field is what is varying. So when we will take derivative of this magnetic field, let me write. When we will take derivative of magnetic field, whose value is 5t cube minus 2t square plus 4t. Now taking derivative, a and n will remain, and we will get 5 times 3, that is 15 t square minus 2 times 2 is 4t plus 4. Now we need to find out the EMF induced at t is equal to 1 second. EMF induced at t is equal to 1 second. That will be a times n. And when we will substitute t is equal to 1, put t is equal to 1, it will be 15 minus 4 plus 4. And putting the value of a and n, a is 50 centimeter square, that is in meters it will be 50 times 10 to the power minus 4 meter square. Number of turns is 200 multiplied by 15. This will be 10 to the power minus 4 times 15. This will be 2, 3, 4, 5. So 10 to the power 5 minus 4 times 15. That means 15, and this will be 10, 150 volt. This will be 150 volt. Am I doing something wrong? This is mistake here. The magnitude of induced EMF in the coil at t is equal to 1 second. 15 times 10, it is coming. 50 times 10 to the power minus 4. 200 times 15. There's the milli somewhere. I don't think so. No, no, wait. Oh, sorry, this is not 10 to the power minus 5. This is 10 to, sorry, I mean, this is not 10 to the power 5. This is 1, 0, 2, 3, 4 zeros are there. Yeah, this is actually, sorry, 10 to the power 4. This is also 10 to the power minus 4. So this will cancel and we'll get 15 volt. 15 volt is the correct answer. Yeah, so these were the concepts and questions related to the experiments and theories that were discussed in today's week. So again, let's have a recap that what all the things that we discussed in today's week. So this week, oh, these were the last week things. This week we talked about actually RC circuit. What is the theory of discharging and discharging, charging and discharging of a capacitor in an RC circuit? Then we understood the magnetic field, the magnitude of magnetic field due to a current carrying circular coil. Here we started with Biot-Savart's law, then find out the magnetic field in current carrying circular coil, then what is the magnetic field value due to two current carrying coils when they are at a distance nearby, or we can say they are at a distance of equal to their radius, and when they are at a distance of half of their radius, then they make the Helmholtz coil, and it lets us achieve a uniform magnetic field in a region. And then we discuss the EMF induced in a coil. So these were the things for this week. We'll meet next week. Thank you.